Multiple representations. A single resource can have multiple representations, each with a different media type. To illustrate, let's look at two different representations of the same contact resource. The first, in figure 2:2, is a JSON representation and contains information about the contact. The second, figure 2:3, is the avatar for the contact. B. Both are valid representations of state, but they have different uses. Figure 2:2. Contact JSON representation. Figure 2:3. CO. Intact PNG representation. The JSON representation will be parsed and data such as the contact name, email address, etc. will be extracted from the JSON and displayed to the user. The PNG representation, however, will just display as is, because it is an image. It could also easily be passed as the URL for an HTML tag or consumed directly by an image viewer. As the previous example shows, the advantage of supporting multiple representations is to allow many different clients with different capabilities to interact with your API. API styles. There are many different architectural styles for building web APIs. By style we mean an approach for implementing an API over HTTP. A style is a set of common characteristics and constraints that permeate the design. Each style has trade-offs and benefits associated with it. The important thing to recognize is that the style is an application of HTTP. It is not HTTP. For example, Gothic is a style applied to architecture. You can look at various buildings and determine which are Gothic because they possess certain qualities, such as ogival arches, ribbed vaults, and flying buttresses. In the same way, API styles share a set of qualities that manifest in different APIs. Today we see a number of styles, but they land in a spectrum with RPC on one side and REST on the other. The Richardson Maturity Model. The Richardson Maturity Model RMM by Leonard Richardson introduces a framework for classifying APIs into different levels based on how well they take advantage of web technologies. Level 0. RPC-oriented, a single URI and one HTTP method. Level 1. Resource-oriented, many URIs, one HTTP method. Level 2. HTTP verbs, many URIs, each supporting multiple HTTP methods. Level 3. Hypermedia resources describe their own capabilities and interactions. The model was designed to classify the existing APIs of the time. It became wildly popular and is used by many folks in the API community for classifying their APIs today. It was not without issue, though. The model was not created to establish a rating scale to evaluate how RESTful an API is. Unfortunately, many took it for just that and began to use it as a stick to beat others for not being RESTful enough. This appears to be one of the reasons why Leonard Richardson himself has stopped promoting it. Throughout this chapter, you will dive more deeply into the different levels of RMM and see real-world examples. We'll use the levels to discuss the benefits and trade-offs as associated with how you design your API. RPC RMM Level 0. At Level 0, an API uses an RPC remote procedure call style. It basically treats HTTP as a transport protocol for invoking functions running on a remote server. In an RPC API, the API tunnels its own semantics into the payload, with different message types generally corresponding to different methods on the remote object and using a single HTTP method, host. The SOAP services, XML RPC, and POX plain old XML APIs are examples of Level 0. Consider the example of an order processing system using POX. The system exposes a single order processing service at the URL/order service. Each client posts different types of messages to that service in order to interact with it. To create an order, a client sends the following Post/order service HTTP 1.1 content type application /XML content length XX. The server then responds, telling the client the order has been created. HTTP/1.1200 OK content type application /XML content length XX. Order created. Notice the status is in the body itself, not via the status code. This is because HTTP is being used as a transport for a method invocation where all the data is sent in the payload. To check on the list of active orders, the client sends a GET orders request. Post/order service HTTP 1.1 content type application /XML content length XX. The server reply contains the list of orders. HTTP/1.1200 OK content type application /XML content length XX. To approve an order, the client sends an approval request. Post/order service HTTP 1.1 content type application /XML content length XX. The server responds, indicating the status of the approval. HTTP/1.1200 OK content type application /XML content length XX. Order approval failed. Missing information. Similar to the status mentioned earlier, here the error code is part of the payload. As you can see from the preceding examples, in this style the payload describes a set of operations to be performed and their results. Clients have explicit knowledge of each of the different message types associated with each service, which they use to interact with it. You might be asking, why not use another method like put? The reason is because in this approach all requests are sent to a single endpoint/order service regardless of the operation. Post is the least constrained in its definition, as it is both unsafe and non-dependent. Each of the other methods, however, has additional constraints, making it insufficient for all operations. One benefit of this approach is that it is very easy and simple to implement and aligns well with the existing development mental model. Resources RMM Level 1. At Level 1, the API is broken out into several resources, with each resource being accessed via a single HTTP method, though the method can vary. Unlike Level 0, in this case the URI represents the operation. Returning to the preceding order processing example, here is how the requests look for a Level 0 API. To create an order, the client sends a request to the Create Order API, passing the order in the payload. Post/create order HTTP 1.1 content type application /JSON content length XX. Order number 1000. The server then responds with an order that has an active status. HTTP/1.1200 OK content type application /JSON content length XX. Order number 1000, status active. To retrieve the orders, the client makes a request to list orders and specifies the filter in the query string. Notice that for retrieval the client is actually performing a GET request rather than a POST. GET/list orders, status equals active. The server then responds with the list of orders. HTTP/1.1200 OK content type application /JSON content length XX. Order number 1000, status active. Order number 1200, status active. To approve the order, the client makes a POST request to the approve order resource. Post/approve order, order number equals 1000. A common example of an API using this style is Yahoo's Flickr API. Looking at the documentation, we see API methods. Looking under galleries, we see the methods listed in Figure 2 to 4. Figure 2 to 4. Yahoo Flickr API. There are several different URIs for working with photos. To add a photo, you'd request the Add Photo API, while to retrieve a photo you can use Get Photos. T. O update a photo. You can request the edit photo or edit photo APIs. Notice this style is still very RPC-ish in the sense that each resource corresponds to a method on a server-side object. H. However, because it can use additional HTTP methods, some resources can be accessed via GET, allowing their responses to be cached as in the earlier list orders example. T. His style provides additional evolvability benefits in that we can easily add new functionality to the system as resources, without having to modify existing resources, which could break current clients. HTTP verbs RMM Level 2. In the previous examples, each resource corresponded heavily to the implementation on the server, relating to one or more methods on server-side objects, thus, those X. Examples were very functionality-oriented get order. A Level 2 system uses a resource-oriented approach. The API exposes one or more resources order, which each support one or more HTTP methods. T. Has types of APIs offer richer interactions over HTTP, supporting capabilities like caching and content negotiation. In these APIs, it is common to have a delineation between collection resources and item resources. A collection resource corresponds to the collection of child resources, e.g., http:// example.com/orders. T. O retrieve the collection. A client issues a GET request to this resource. T. O add a new item to the collection. A client posts an item to this resource. An item resource corresponds to an individual child resource within a collection. E.g., http://example.com/orders/1 corresponds to order 1. To update the item read. Source, a client sends a put or patch request. To delete, it uses a delete method. It is also common to allow put to create the resource if it does not exist. An item resource is generally referred to as a sub-resource, because its URI implies a hierarchy. I.e., in /orders/1, the 1 is a child. Both collection and item resources can have one or more collection and item read sources as children. Applying the order example to level style, the client now sends the following request to create an order. Post/orders content type application/JSON content length XX. Order number 1000. The server then responds with a 201 created status code and a location header indicating the URI of the newly created resource. The response also includes an e-tag header to enable caching. http://1.1201 created location/orders/1000 content type application/JSON content length XX e-tag 12345. Order number 1000, status active. To list active orders, the client sends a GET request to the /active subresource on dir/orders. Get/orders/active content type application/JSON content length XX. Order number 1000, status active. Order number 1200, status active. To approve the order, the client sends a put request to /orders/1000/approval. Put /orders/1000/approval. The client then responds, indicating in this case that the order approval has been rejected. http://1.1403 forbidden content type application/JSON content length XX. Error. Code 100, message missing information. Looking at the preceding examples, you can see the difference in the way the client interacts with such an API. It sends requests to one or more resources using the HTTP methods to convey the intent. A real-world example of a resource-oriented API is the GitHub API. It exposes root collection resources for each of the major areas in GitHub, including orgs, repositories, pull requests, issues, and much more. Each collection resource has its own child item in collection resources. To interact with each resource, you use standard HTTP methods. For example, to list repositories for the current authenticated user, we can send the following request to the repos resource. Get http://api.github.com/users/repos/http/1.1 to create a new repository for the current authenticated user. We issue a post to the same URI with a JSON payload specifying the repo information. Post http://api.github.com/users/repos/http/1.1 content type application/JSON content lengths. Name new repo. Description: this is a new repo. Homepage: https://github.com. Private false. Has assumes true. Password key true. Has downloads true. Crossing the chasm toward resource-centric APIs. Designing resource-oriented APIs can be challenging, as the noun-centric/non-object-oriented style is a big paradigm shift from the way developers traditionally design procedural or object-oriented APIs in 4 gallons programming languages. The process involves analyzing the key elements of the system that clients need to interact with and exposing those as resources. One challenge API designers face when doing this is how to handle situations where the existing set of HTTP methods seems insufficient. For example, given an order resource, how do you handle an approval? Should you create an approval HTTP method? Not if you want to be a good HTTP citizen, as clients or servers would never expect to deal with an approval method. There are a couple of different ways to address this scenario. Have the client do a put/patch against the resource and have approved equals true included as part of the payload. It could be either in JSON or even a form URL encoded value passed in the query string. Patch http://example.com/orders/1. Approved equals true http://1.1. Factor out approval as a separate resource and have the client post or put to it. Post http://example.com/orders/1/approval http://1.1. Hypermedia RMM Level 3. The last level in Richardson scale is hypermedia. Hypermedia are controls or affordances present in the response that clients use for interacting with related resources for transitioning the application to different states. Although RMM defines it as a strict level, that is a bit misleading. Hypermedia can be present in an API, even in an RPC-oriented one. The origins of hypermedia on the web. Hypermedia and hypertext are concepts that are part of the very foundations of the web and HTTP. In Tim Berners-Lee's original proposal for the World Wide Web, he spoke about hypertext. Hypertext is a way to link and access information of various kinds as a web of nodes in which the user can browse at will. Potentially, hypertext provides a single user interface to many large classes of stored information such as reports, notes, databases, computer documentation, and online systems help. He then went on to propose the creation of a new system of servers based on this concept, which has evolved to become the World Wide Web. We propose the implementation of a simple scheme to incorporate several different servers of machine-stored information already available at server, including an analysis of the requirements for information access needs by experiments. Hypermedia is derived from hypertext and expands to more than just simple documents to include content such as graphics, audio, and video. Roy Fielding used the term in Chapter 5 of his dissertation on network architecture, where he discusses representational state transfer REST. He defines right off the bat that hypermedia is a key component of REST. This chapter introduces and elaborates the representational state transfer REST AR architectural style for distributed hypermedia systems. There are two primary categories of hypermedia affordances: links and forms. To see the role each plays, let's look at HTML. HTML has many different hypermedia affordances, including and tags. When viewing an HTML page in a browser, a user is presented with a set of different links from the server that are rendered in the browser. Those links are identified by the user via either the link description or an image. The user then clicks the links of interest. The page can also include forms. If a form is present, such as for creating an order, the user can fill out the form fields and click Submit. In either case, the user is able to navigate the system without any knowledge of the underlying URI. In the same way, a hypermedia API can be consumed by a non-browser client. Similar to the HTML example, the links and forms are present but can be rendered in different formats, including XML and JSON. For more on forms, see Hypermedia and Forms. On Code Better. A link in a hypermedia API includes a minimum of two components: a URI to the related resource, a rel that identifies the relationship between the linked resource and the current resource. The rel and possibly other metadata is the identifier that the user agent cares about. The rel indicates how the resource to which the link points relates to the current resource. Measuring hypermedia affordances with H-factors. Mike Amundsen has created a measurement called an H-factor designed to measure the level of hypermediacy effort within a media type. H-factors are divided into two groups with their own factors. Link support, LE embedding links, LO outbound links, LT templated queries, LN non-idempotent updates, LI idempotent updates. Control data support. CR control data for read requests. CU control data for update requests. CM control data for interface methods. CL control data for links. H-factors are a useful way to compare and contrast the different types of hypermedia APIs that exist. Returning to the order example, we can now see how hypermedia will play in. In each of the aforementioned scenarios, the client has complete knowledge of the URI space. In the hypermedia case, however, the client knows only about one root URI, which it goes to in order to discover the available resources in the system. This URI acts almost like a home page. In fact, it is a home resource. Get/home accept application/JSON profile equals http://example.com/profile/orders. In this case, the client sends an accept header with an orders profile. http://1.1200 OK content type application/JSON profile equals http://example.com/profile/orders. Content length XX. Links. Rel orders, ref/orders. Rel shipping, ref/shipping. Rel returns, ref/returns. The home resource contains pointers to the other parts of the system, in this case, orders, shipping, and returns. To find out how to interact with the resources that the links point to, the developer building the client can reference the profile documentation at the profile URL just indicated. The document states that if a client sees a link with a rel of orders, it can post an order to that resource to create a new one. The content type can just be JSON, as the server will try to determine the correct elements. Post/orders content type application /JSON content length XX. Order number 1000. Here is the response. http://1.1201 created location /orders /1000 content type application /JSON. Profile equals http://example.com/profile/orders. Content length XXE tag 12,345. Order number 1000. Status active. Links. rel self. ref/orders/1000. rel approved. ref/orders/1000/approval. rel cancel. ref/orders/1000/cancellation. rel hold. ref/orders/1000/hold. Notice that in addition to the order details, the server has included several links that are applicable specifically for the current order. Self identifies the URL for the order itself. This is useful as a bookmark to the order resource. Approve identifies a resource for approving the order. Cancel identifies a resource for placing a cancellation. Hold identifies a resource for putting the order on hold. Now that the client has the order, it can follow the approval link. The profile spec indicates that the client should do a put against the URL associated with a rel of ap-prove in order to approve the order. Put/orders/1000/approval content type application /JSON. The response will be identical to the level 2 response. http://1.1403 forbidden content type application /JSON. Profile equals http://example.com/profile/orders. Content length XX. Error. Code 100. Message missing information. PayPal recently introduced a new payments API that incorporates hypermedia in its responses. The following is an extract of a response for a payment issued using the new API. Links. Ref https://api.sandbox.paypal.com/v1/payments/sales/1k480. rel self. Method get. Ref https://api.sandbox.paypal.com/v1/payments/sales/1k480/refund. rel refund. Method post. Ref https://api.sandbox.paypal.com/v1/payments/payment/pay34629814w. rel parent payment. Method get. As you can see, it contains the self link mentioned previously, as well as links for submitting for a refund and accessing the parent payment. Notice that, in addition to the standard ref and rel members, each link contains a method member that advises the client on which HTTP method it should use. In this case, the media type PayPal returns as application/JSON. This means the client cannot simply tell by the response headers that the payload is in fact a PayPal payload. However, the PayPal documentation explains the rel, and that it is possible to navigate the system without hard coding against URLs. In each of the previous examples, hypermedia provides the benefit that the client has to know only a single root URL to access the API and get the initial response. From that point on, it follows its nose by navigating to whatever URLs the server serves up. The server is free to change those URLs and offer the client specifically targeted links without affecting other clients. As with all things, there are trade-offs. Implementing a hypermedia system is significantly more difficult, and is a mind shift. More moving parts are introduced into the system as part of the implementation. In addition, using hypermedia-based approaches for APIs is a young and evolving science, so you do have some of your work cut out for you. In many cases, the trade-off is worth it, in particular if you are building an open system that needs to support many third-party clients. REST, or representational state transfer.